a time for undisputed king of machine learning, Andrew NG. Andrew, I don't know what is a good Andrew Notorious NG.
That we talked about on Wednesday, talked about on Monday. You're trying to minimize the norm of W, and then there was this additional parameter C that trades off how much you.
Oh, wait. We were talking about regularization. We were talking about the lambda parameter, minimizing, like adding this norm of theta. And we were talking about, we have training set, test set, and I guess that's evaluation set. And we were talking about if you overfit, it works great on your train set, probably bad result on another data set which is test set. And if you underfit, we won't have even good result on our training set.
Find every training example perfectly. So whether you're trying to make, which of these decisions you're trying to make, how do you choose a polynomial size, or choose lambda, or choose tau, or choose parameter C, which also has this bias variance trade-off. There are some values of C that are too large and some values of C that are too small.
C is too large. C. What was C? Size.
So here's one thing you can do, which is let's see. So split your training data S into a subset.
I didn't go to gym for 2 days, by the way.
Your training set S subscript train, and then some subset which we want to call S subscript dev, and dev stands for development.
Dev stands for
and
development.
We'll talk about a separate test set. And so what you can do is train each model, and by model I mean option.
By model, he means option.
For the degree of polynomial.
So he's saying we have a third data set, fourth data set, development.
On S train, so if you're evaluating a menu of models, right? So let's say this is model 1, model 2, and so on, up to model 5, up to some number. Then you can train each of these models on the first subset of your data, and then get some hypothesis. Let's call it HI. And then measure the error on SDEV, which is the second subset of your data called the development set, and pick the one
Train each model in option.
Okay. So rather than I want to contrast
so
this.
So we have a train set and development set,
procedure, right? So
and we add actually, and we do 2 models, and we choose one of those models.
That's the data, 2 subsets of data. Let's talk about test set data. Training set and development set. And after training, first one polynomial, second one polynomial, third one polynomial on the training set, evaluate all of these different models on a separate held up development set, and then pick the one with the lowest error on the development set. Okay? But the one thing to not do would be to evaluate all these algorithms instead on the training set, and then pick the one with the lowest error on the training set. Right? Why not? What goes wrong when you do that?
What happened? I didn't listen.
Oh,
So it says it is not good to get the one with the lowest
and then some subset,
error.
which one
Overfitting.
has
Overfitting
dev,
happens,
and
right?
dev stands for development. and then later we'll talk about a separate test set. And so what you can do is train each model, and by model I mean option for the degree of polynomial.
Okay.
On S train. So if you're evaluating a menu of models, right? So let's say this is model 1, model 2, and so on, up to model 5, up to some number. Then you can train each of these models on the first subset of your data,
String.
and then get some hypothesis. Let's call it HI. And then measure the error on SDEV, which is the second subset of your data called the development set,
So development.
and pick the one.
So it says pick the one with the lowest error on SDEV. Oh, I see. Okay, good. Like, right? So it seems like we divided our training set to two smaller one, which the first one we still call them the training. Second one, we call it development data set. And here because as I said at the beginning, if we do we make a model with a lot of parameters, right? If you make a model with a lot of parameters, what happens is it overfits on training set. It has no error, or as small as the more complex the model is, the error is less on the training set, obviously. So here we say, okay, we divided our training set. Now we have different levels of complexity for our models, and on the second part of our training set, we implement those models, and the one with the least on the development data set will be chosen. If you choose the one with the least error on the training data set, that would be the most complex one.
So rather than, I want to contrast this with an alternative procedure, right? So the two sets of the data, two subsets of data. Let's talk about test set data, training set and development set. And after training, first order polynomial, second order polynomial, third order polynomial on the training set, evaluate all of these different models on a separate product development set, and then pick the one with the lowest error on the development set. Okay. But the one thing to not do would be to evaluate all these algorithms instead on the training set, and then pick the one with the lowest error on the training set. Right? Why not? What goes wrong when we do that? Yeah, right. You just overfit. Why were you overfit? Yeah, cool, right. So if you use this procedure, you always end up picking the fifth order polynomial, right? Because the more complex algorithm will always do better in the training set. So if you do this, this will always cause you to say, let's use the fifth order polynomial, or the highest possible order polynomial. So this won't help you realize in the housing price prediction example, the second order polynomial is a benefit to the data. Right? That makes sense? And that's why for this procedure, if you evaluate your model's error on a separate development set that the algorithm did not see during training, this allows you to hopefully pick a model that neither overfits nor underfits. And in this example, hopefully you find that it'll be the second order polynomial, right? The one that's just right in between that actually does best on your development set. Okay. Now, and then, you know, if you are publishing an procedure has looked at the training set as well as the development set, right? So this procedure, this piece of code is, is tuned its decisions, is tuned the parameters, the training set, and is tuned the decision on the degree of polynomial to the dev set. And so if you want to know, if you want to publish a paper to say, oh, my algorithm achieves 90% accuracy of this data set, it's not valid to report the result on the dev set because the algorithm has already been optimized to the dev set. In particular, information about what's the best degree of polynomial to choose was derived from the dev set, from the development set. And so if you're publishing a paper or you want to report an unbiased result, evaluate the algorithm on a separate test set as test, and report that error. Okay? And so if you're publishing a paper, it becomes a good hygiene to report the error on a completely separate test set that you did not in any way, shape, or form look at during the development of your model, during the training procedure. Okay? Make sense?
Who is that
the
student?
Who
is that
It depends on the size of the data set. And so it turns out that, actually, let me give an example. Actually, so let's say you're trying to fit a degree of polynomial.
Smells.
And you want to choose, right, the dev error. So for the first, second, third, fourth, fifth degree polynomial. And so after fitting all of these,
What are the
let's say
options?
that the squared error.
What are the options?
Right.
What are the options other than saying smells fucking good? I don't want to use the fucking.
If you're looking for different ways to express that something smells really good, you can
Really?
say, 1, this smells amazing.
Amazing.
2, wow, this has a wonderful aroma. 3, it smells delightful. This is so fragrant and pleasant. 5, the scent is absolutely heavenly. These are all polite and positive ways to express that something has a very pleasing smell. Do you have a specific context in mind for using these expressions?
Why do I always use the fucking to emphasize?
It sounds like you're noticing a habit of using strong language, particularly the word fucking, in your speech. This can happen for a few reasons. 1, habit. Sometimes, if you're used to speaking a certain way, or you're often around others who use similar language, it can become a habitual part of your speech. 2, emphasis. People often use strong language to emphasize their feelings or opinions. 3, expression. It can also be a way of expressing strong emotions, like frustration, excitement, or passion. If you're looking to change this habit, a good first step is being aware of it, as you already are. Then, you can try to pause before you speak. Think of alternative words, or practice phrases that convey your feelings without using strong language. Would you like tips on how to reduce the use of strong language in your speech?
Yeah, give me that, baby.
All right. Here are some tips to help reduce the use of strong language. 1, pause before speaking. Take a moment to think before you speak. This gives you a
That
chance
is
to
not
choose
good.
your words more carefully.
I don't want to
2,
do that.
find alternatives.
Think before you talk.
Words or
No.
phrases that can express what you feel. For example, instead of saying, this is fucking amazing, you might say, this is absolutely amazing, or this is incredibly
Absolutely.
good.
Incredibly.
Practice
Absolutely.
mindfulness. Being more aware of your thoughts and feelings can help you control your reactions and the way you express
Absolutely.
yourself.
Incredible.
Slow down. Sometimes
Then
speaking
I
more
will say
slowly
incredible,
helps you choosing
you.
words more thoughtfully. 5, seek feedback. Ask friends or family to gently remind you when you.
If you're using the dev error to pick,
Speaking slowly. That I can do. Like instead of thinking, pause before speaking. Take a moment to think before you speak. Find alternatives. Absolutely, incredibly, Mindfulness. What is mindfulness? Being more aware of your thoughts and feelings can help you control your reaction, the way you express yourself. Slow down, seek feedback. Ask friends or family to gently remind you when you use a strong language. Read and listen.
The best hypothesis. to
What
make
does that
ourselves
mean?
You would say
Expose
that,
yourself to a variety of
using
language,
the
use it
1.0
like books,
gets
podcasts, so
you 4.9
your
squared
own
error,
speech pattern.
right? But did you
Takes
know
time,
that
guys.
4.9
It takes
squared error?
incredibly
Did you just get
times.
lucky?
It
There is
absolutely
some
takes
noise,
time.
and so
So don't
in
expect
all
me
these
right
things,
away.
that error, that close to 5.0,
And be
there's
patient
some
with
which is higher, some which is
yourself.
lower, and you just
Would
got
you like
lucky
more specific
that the dev
advice?
set just did better. Which is why if you look at your dev set error, your dev set error is a biased
I
estimate.
have this
So
feeling
whereas a very large test set, there's a very large test
beside
set,
my
maybe the true numbers are 10, 5, 5, 5, 7, 10 are your actual expected square errors. It's just that
strength.
because a little bit of noise, you got lucky and you reported 4.9. And so this would be a bad thing to do in an academic paper, right? Because so what you earned was an error of 5.0, you didn't earn an error of 4.9. It's just that because you're overfitting a little bit to the dev set, you chose the thing that looked best for the dev set, and the algorithm didn't actually get that error. It's just because of noise.
No more done.
So now so it's considered good practice to report. So reporting on the dev error isn't really a valid, unbiased procedure, and then.
Who checks where is the data set coming from? Like even if you report on your tests, who is checking that? Absolutely, absolutely, absolutely.
So one of the, just to be said, I guess you
Incredibly.
problems with some of the machine learning benchmarks that people worked on for a long time is there's this unavoidable mental overfitting that people got to use the data set and everyone's
Unavoidable.
trying to publish the best numbers of the same test set. So the academic community on machine learning does have some amount of overfitting to the standard benchmarks that people have worked on for a long time. And this is an unfortunate result. When the test set is very, very large, the amount of overfitting is probably smaller. But when the test set is not big enough, then the overfitting result can cause sometimes even research papers to publish results that are primarily overfit to the data set. Right? And so I think there's actually one standard academic benchmark is a data set called CFAR. It's quite small. So there's actually a very interesting research paper analyzing results on CFAR, arguing that some fraction of the progress that was made was actually perhaps researchers unintentionally overfitting to this data set.
Can happen.
Oh, and by the way,
Isn't it funny that we have papers on
building,
them?
Production machine learning
For
systems.
me, that everything should be like mathematically proved. These are kind of interesting. We can have papers that are published. Well, I think even we can have papers that are proven, but like they're mathematically wrong, but the committee couldn't check the correctness. But here they have papers that are like experimental. But that number can be much higher, I guess.
When I'm shipping a product, right, I just want to build a speech recognition system and just make it work. I just want to, and if I'm not trying to publish a paper and not trying to make some claim, sometimes I don't bother to have a test set, right? So, and it means I don't know the true system. So, and the data set called CFAR. It's quite small. So it's actually a very interesting research paper analyzing.
So sometimes we don't need a.
Arguing that.
Oh, we are not publishing. We are not proving to other people that our
perhaps researchers
algorithm is working good. So then you don't need to have.
Oh, and by the way, one thing I do when I'm building, production machine learning systems. So when I'm shipping a product, right, I just want to build a
Product.
system and just make it work. I just want to, and if I'm not trying to publish a paper, I'm not trying to make some claim, sometimes I don't bother to have a test set, right? So and
Yeah, it doesn't make sense because if you're producing a product, what does test set mean? Test set means if you have a test set will be another development data set. Because then you have to work on the product.
That means I don't know the true error of the system sometimes, but I'm very conscious of that. If I don't log data, sometimes I'm gonna decide to just not have a test set, and it means I just don't try to report the test set number. I can report the dev set number, which I know is biased, and I just don't report the test set number. I don't do this if you're publishing an academic paper, right? This is not good if you're publishing a paper or making claims on the outside, but all we're doing is building a product and not writing a paper. This is actually
Yeah, it makes sense. Well, what would be? All of the students in this class are.
That's let me get to that. Okay. So the next topic about setting up the train dev test splits is how do you decide how much data should go into each of these three subsets? I can so let me just tell you the historical perspective and then a modern perspective. Historically, the rule of thumb was you take a training set, right? You take your training set S, and then you would send. One rule of thumb that you see a lot of people refer to is 70% training,
Ooh,
right? 30% tests.
I see.
This is one common rule of thumb that you just hear a lot. Or maybe you have, if you don't have a dev set, if you're not doing
30%
model search,
train.
if you already picked a model, not very well. Or maybe you have people use 60% train, 20% dev,
20%
20%
test.
test.
Mm-hmm.
Right? So these are rules of thumb that people use to give.
70-30 or
And
60-20.
These are decent rules of thumb when you don't have a massive data set. Say if you have 100 examples, maybe 1,000 examples, maybe several thousand examples, I think these rules of thumb are perfectly fine. What I'm
Massive.
seeing is that as you move to machine learning problems with really, really giant data sets, the
Training
percentage
should
of
be
data
small.
you send to dev and test are shrinking. Right? And so here's what I mean. Let's say you have
They are
10
shrinking?
million examples.
Use 10.
Decent size, not giant, but reasonable size. So let's take this. This is actually a pretty good rule of thumb if you're a small data set. If you have 500 examples, this is a perfectly fine rule of thumb to use. But if you have 10 million examples, then you have 6 million, 2 million.
Okay. I feel when your
2 million.
data set is very big, you want to have a smaller training set because just building the model based on that training set would take a long time also if you want to.
And the question is, do you really need 2 million examples to estimate the performance of your final classifier? Sometimes you do.
It's just,
if
yeah,
you-
actually that's the whole thing. I say let's have, well, we can remove test because it will be similar. We will set the training set. We can have 2 test sets, but all of them are a small subset, and the rest will be a real world situation, and we don't care about. Unless like something like that. There's no.
You're working on online advertising, which I have done, and you're trying to increase your ad click-through rate by 0.1%, because it turns out increasing ad click-through rates by 0.1%, which I've done multiple times, turns out to be very lucrative. You actually need a very large data set to measure these very, very small improvements. Because to increase an ad click-through rate by 0.1, you might actually have a lot of projects. You might have 10 projects, each of which increases ad click-through rate by 0.01%, right? And so to measure these very small differences in algorithm 1 does 0.01% better than algorithm B, but so you need a lot of data to tease out that very small difference. So if you're in the business of teasing out these very small differences, you actually need very large test sets. But if you're comparing different algorithms, and one algorithm is, 2% better, or even 1% better than the other algorithm, then with 1,000 examples maybe, right? 1,000 examples may be enough for you to distinguish between these much larger differences. So my recommendation for choosing the dev and test sets is choose them to be big enough.
Big enough.
That you have enough data to make meaningful comparisons between different algorithms. And if you suspect your algorithms will vary in performance by 0.01%, you just need a lot of data to distinguish that, right? So if you have 100 examples, then if one algorithm has 90% accuracy and one algorithm has 90.01% accuracy, then unless you have at least 1,000 examples or maybe 10,000 or more, you just can't see this very small difference, right? If you have 100 examples, you just can't measure this very small difference. So my advice is choose your dev and test sets to be big enough that you can see the differences in the performance of algorithms that you roughly expect to see. And then you don't need to make your dev and test sets much larger than that. And I would usually then just put the data, you don't need the dev and test sets back in the training set. So when you're working with very large data sets, say million, 10 million, 100 million examples, what you see is that the percentage of data that goes into dev and test tends to be much smaller. So it might be, so you see, for example, maybe 90% train, 5% dev and 5% test, right? Or even smaller, or even 1%, depending on how much data you really need.
Oh, so he's saying let's do 90% training. That doesn't sound right. Actually, we have too much data to build the model. That's what I believe. And I believe I have to get a haircut. It's getting out of control. So I don't like this. I don't like 90%. Wait a second. Where is this model going to work? Why should we get so many data, like from the beginning? If you have maybe, I don't know, like this DNA stuff, like from the beginning they start from, I don't know, a big number, 1 million, and then you need to have, today get something that is reasonable and you can make it model, then build it and go.
To measure to the level of accuracy you need, the differences in performance of your algorithms. Okay. All right. Just to give this whole procedure a name, what we just did here between the train and dev set, this procedure that we have is called hold-down cross-validation. And sometimes, to distinguish this from other cross-validation procedures we'll talk about later, sometimes this is called simple hold-down cross-validation. We'll talk about some other hold-down cross-validation procedures in a second. And the dev set is sometimes also called the cross-validation set.
Oh, okay. Cross-validation is the develop set. So we develop, instead of one model, we develop multi-number of models. And develop set has this difference with the test set, that for develop set, we are choosing between different models. So it is like optimization over optimization, kind of. Development is cross-validation. Hold out cross-validation. Simple. What is one?
As did here, between the train and dev set, this procedure that we have is called hold-down cross-validation. And sometimes, to distinguish this from other cross-validation procedures we'll talk about in a minute, sometimes this is called simple hold-down cross-validation. We'll talk about some other hold-down cross-validation procedures. And the dev set is sometimes also called the cross-validation set.
I didn't listen to him again. What the fuck? What is it called?
To measure to the level of accuracy.
So it should be 95.5.
Okay. All right. Just to give this whole procedure a name, what we just did here between the train and dev set, this procedure that we have is called holdout cross validation.
Okay, this procedure is called holdout cross validation. And cross validation is development set.
And sometimes, to distinguish this from other cross validation procedures we'll talk about in a minute, sometimes this is called.
Oh, they're going to talk about
cross validation. We'll talk about some other holdout cross validation procedures in a second. And the dev set is sometimes also called the cross validation set. So sometimes
Don't
people
fall,
use,
motherfucker.
sometimes you hear people say, you know, I'm going to use a cross validation set. That means roughly the same thing as a dev set.
Do you think it depends on the place of it on the table?
So in the normal workflow of developing a learning algorithm, when you're given a data set, I was
I hear three big noise.
Oh, and I used to say cross-validation set, but cross-validation is just a mouthful. So I think just motivated by the reducing number of
Feel
students
free.
who's using the concept so often, more people just call it dev set. It's roughly the same thing, right? So
I don't think it
when
depends.
I'm building a machine learning system, I'll often take the data set, split into train and train, and if you need a test set, then also
Anyway.
a test set, and then keep on fitting the parameters to the training set and evaluating the performance of the algorithm of the dev set, and so I'm using that to come up with new features, choose the model size, choose the regularization parameter, the lambda, really try out lots of different things and spend, you know, several days or weeks to optimize the performance of the dev set. And then when you want to know how well is your algorithm performing, to then evaluate the model on the test set, right? And the thing to be careful not to do is to make any decisions about your model using the test set, right? Because then you assign to fit the data to the test set and it's no longer non-biased.
Yes, that's right.
So
He said it in a
one thing
dual
that is
way.
actually
For a
okay
second,
to
it was
do
weird.
is, if you have a team that's working on a problem, if every week they measure the performance of the test set and report out on the chart, right? You know, the performance of the test set. That's actually okay. You can evaluate the model multiple times on the test set. You can actually give them a weekly report. Say this week for our online advertising system, we have this result on the test set. 1 week later, with this result on the test set.
Why is it okay?
It's actually
Why is it okay? Because the problem is that we don't want test set have a feedback or a loop into our model. Test set should not be part of the input to the function that we make the model with. So once in the company, my company, we are developing different algorithms. Actually, it is good to have this chart because we can say, okay, we can compare these models on this test set. We can always compare models on the training set as well. But if we say test set stands for the real world problem, it will be a better comparison maybe.
okay to evaluate your algorithm repeatedly on the test set. What's not okay is to use those evaluations to make any decisions about your learning algorithm. So for example, if one day you notice that your model is doing worse this week than last week on the test set, if you use that to revert back to an older model,
I
then
see.
you just made the decision that's based on the test set.
How can you say you did not? Because always, all the time you say that, right? If you're doing it and you're human beings and say, okay, this model got better, next time you're developing a model, you're trying to fit into your test set, which is not good. Unintentionally, maybe.
And your test set is no longer biased. But if all you do is report out the result, but not make any decisions based on the test set.
Dude, I should do
such as
something
what
with
the
my hair.
early model, then you can. It is actually legitimate. It's actually okay to keep on, use the same test set to track your team's performance over time. Okay. All right. Good.
Alright, good.
So when you have very large data sets, this is a procedure for defining the train depth and test sets, and this procedure can be used to choose the model or polynomial. It can also be used to choose the regularization parameter lambda or the parameter c.
Parameter C, the lander,
Now, what if you have a very small
one of the very small, very small data sets.
So it turns out that
Oh wait, okay. So we had 70-30-30, and we had 95-5, and we had some cross-validation issues, and we had not using test set to build the model because it is just against what everything we started, and what test set stands for. And now what happens if we have very small data sets? We cannot train well if the data set is very small. We cannot train well.
so now I'm going to leave out the test set for now, right? Let's just assume there's some separate test set. We're not going to worry about that for now. But let's say you have 100 examples, right?
We do
If
the
you
best we
split
can do.
this into 70 in the training set in S subscript train and 30 in S dev, then you're training your algorithm on 70 examples instead of 100 examples. And so I've actually worked on a few healthcare problems. Actually, most of my PhD students, including on it, right, are doing a lot of work on machine learning applies in healthcare. And so we're actually working on a few data sets in healthcare where, every training example corresponded to some patient that sometimes had a
We don't have-
disease, or if every
We don't have enough data sets.
or if every
Data
example
points.
corresponded to injecting a patient with a drug and seeing what happens in patient. Sometimes there's literally a lot of blood and pain that goes into collecting every example. And if you have 100 examples, to hold out 30 of them for the purpose of model selection, using only 70 examples and 100 examples, it seems like you're wasting a lot of data that was collected through a lot of literal pain.
What do you mean it seems?
So is there a way to, say, do model
Well, it
selection?
is when you have development set, it looks like it's a two-stage optimization method, right? I don't get what he means by it seems.
Such as choose the degree of polynomial without, quote, slightly wasting so much of the data. There's a procedure that you should use only if you have a small data set, only if you're worried about the size. And the other disadvantage of this is you're evaluating your model only on 30 examples, and that seems really small, right? Can you just find more data to evaluate your models as well? So there's a procedure that you should use only if you have a small data set called k-fold cross-validation.
K-fold
And
cross-validation.
this is in contrast.
Okay, so K-fold cross-validation. We are going to memorize this shit. We are going to put it in our mind brain. K-fold cross-validation for a small data.
It's a simple cross-validation. But this is the idea, which is, let's say this is a training set S, so you have x1, y1, down to x, say 100, y100. What we're going to do is take the training set and divide it into k pieces. So for the purpose of illustration, I'm going to use variables 5, just to make the writing on the board same. K equals 10 is typical. Right? Because for illustration. So what you do is take your data set and divide it into 5 different subsets. In this example, you would have 20 examples. 100 examples divided into 5 subsets, so there are 20 examples in each subset. And what you do is, for I equals 1 to k, train, i.e. fit parameters, on k minus 1 pieces, and then test on the remaining one piece, and then you average, right? So in other words, when k is equals 5, we're going to loop through 5 times. In the first iteration, we're going to train on these and test on the last 1/5 of the data. So we'll hold up the last 1/5 of the data, train on the rest and test on that. And then in the second iteration, through this for loop, we'll train on pieces 1, 2, 3, and 5, and test on piece number 4, and we'll get the number.
Okay.
And then you hold out this third piece, train on the others, test on this, and so on. So you do it 5 times, where on each time you leave out 1/5 of the data, train on the remaining 4/5, and you evaluate the model on that final 1/5.
All right.
Okay. And so if you're trying to choose a degree of polynomial, what you would do is, I guess, for d equals 1 to 5.
Because the data set is small, probably we can't do this. Otherwise, the computation cost will be huge.
Right? So you do this procedure for a first order polynomial. You fit the linear regression model 5 times, each time on 4/5 of the model and test the remaining 1/5. And you repeat this whole procedure for the quadratic function, repeat this whole procedure for the cubic function, and so on.
Ooh,
And
because the data set is small. Guys, I'm telling you. Because the data set is small, we can't do that. Otherwise,
Is for every order polynomial from 1, 2, 3, 4, 5, you would then pick the degree of polynomial that, and then for each of these models, you then average the 5 S's you have for this error, okay? And then after doing this, you would pick the degree of polynomial that did best according to this model. Okay? And then maybe you find that the second order polynomial does best. And now you actually end up with 5 classifiers, right? Because you now have 5 classifiers, each one fits on 4/5 of the data. And then
we also have
there's a
something I heard. We also have k nearest neighbors, which I don't know what it is exactly, but it is something else, I guess.
you actually end up with 5 classifiers, right? Because you now have 5 classifiers, each one fits on 4/5 of the data. And
K
then,
means
and there's a final optional step, which is to refit the model on all 100% of the data. Okay. So if you want, you could keep 5 classifiers around and output their predictions, but then you're keeping 5 classifiers around. It's maybe a bit more common now that you've chosen to use a second order polynomial to just refit the model once on all 100% of the data. Okay. And so the advantage of k-fold cross-validation is that instead of leaving out 30% of your data for your dev set on each iteration, you're only leaving out 1/k of your data. I use k equals 5 for illustration, but in practice, k equals 10 is by far the most common choice that we use. I've sometimes seen people use k equals 20, but quite rarely. But if you use k equals 10, then on each iteration, you're leaving out just 1/10 of the data, 10% of the data, rather than 30% of the data. Okay? And so this procedure, compared to simple cross-validation, it makes more efficient use of the data because you're holding out only 10% of the data on each iteration.
When it says more efficient, I think it just means when they do the learning in experiment, they see better results. There's no proof that it's like experimental. One thing I want to remember, guys, we didn't cover much today. I'm not happy. I got distracted so many times. Anyways, the k-fold, what we do is every time one case of the data set, we take it as the test set, and the rest is training set. And what we do, okay, we did over these different test sets. What will be our model? Will it be the average? Will it be? I missed that part.
On the remaining one piece, and then you average. Right?
You average,
So
alright.
in other words, when
Alright,
case
you
is
average.
5, we're going to loop through 5 times. In the first iteration, we're going
And
to
then the next thing I missed was that, okay, we had this training set, development set, which was a 2-stage optimization. We did for different levels of complexity, and then we choose the one that is working best for our development set. Now he says, because we are doing one case, something like that, we don't need development or something like that. I want
Train
to
on
look
these.
at that part.
and test on the last 1/5 of the data. So we'll hold up the last 1/5 of the data, train on the rest and test on that. And then in the second iteration, through this for loop, we'll train on pieces 1, 2, 3, and 5, and test on piece number 4, and we get a number. And then you hold out this third piece, train on the others, test on this, and so on. So you do it 5 times, where on each time you leave out 1/5 of the data, train on the remaining 4/5, and you evaluate the model on that final
Alright,
1/5.
okay. And then take the average.
And so, if you're trying to choose the degree of polynomial,
Well,
what
okay.
you would do,
Take the average. Okay, what the fuck? Choose the degree of polynomial.
is, I guess, for, d equals 1 to 5, right? So you do this procedure for a first order polynomial.
So, okay, when he says d, we have d 1 to 5, degree of polynomial. We also have k, which is the how many folds. Okay, but he says once, we can say k is d, something like that.
Fit the linear regression model 5 times, each time on 4/5 of the model and test the remaining 1/5. And you repeat this whole procedure for the quadratic function, repeat this whole procedure for the cubic function, and so on. And after doing this for every order of polynomial from 1, 2, 3, 4, 5, you would then pick the degree of polynomial that, and then for each of these models, you then average the 5 S's you have for this error.
Yes.
Okay. And then after doing this, you would pick the degree of polynomial that did best according to this metric, right? And then maybe you find that the second order polynomial does best. And now you actually end up with 5 classifiers, right? Because you now have 5 classifiers.
Wait, why are we ending up with 5 classifiers? Right. We found out that degree 2 polynomial is the best, right? We found out that degree 2 polynomial is the best. How many folds do we have? How many folds do we have? We have, well, k, d is 2, k is something else. It doesn't matter because degree 2 at the end was decided based on taking the average. Why does he say we have 5? We are left with 5 classifiers. Okay, okay. Because d is 1 to 5, okay. Because we are finding classifier or model for degrees 1 to 5, right? We are finding them for each degree 1 to 5 for each of these d's. We divide the data set to k-fold, do that. For each d, I have a model. And then I'm going to do, well, we don't have a development test though. Development data set.
Right? And then maybe you find that the second order polynomial
Okay.
does best.
We have 5 classifiers. I got this part, right?
And now you actually end up with 5 classifiers.
All right.
Because you now have 5 classifiers, each one fits on
Which
different
one
pieces
is
of
good?
data. And then there's a final optional step,
Optional.
which is to refit the model
Refit the model.
on all 100% of the data. Okay. So if you want, you could keep 5
Optional. Refit the model on the 100% of the data. What does that mean? What does it mean? Refit the model on the 100? Well, we found the model. What does refitting the model, what does that mean? I have no idea.
classifiers around and output their predictions, but then you're keeping 5 classifiers around. It's maybe a bit more common now that you've chosen to use a second order polynomial to just refit the model once on all 100% of the data. Okay. And so the advantage of
Wait, I see. So I think it says you have 5 classifiers, degree 1, degree 2, 5, right? And we want to choose one of these 5s. We don't want to keep all of them. Like the second stage of optimization, like we did with development. So we implement those models on the whole data set now, and whoever has the least amount of error, degree 1, degree 2, degree 5, whoever has the least amount of error will be our chosen model.
K-fold cross-validation is that instead of leaving out 30% of your data for your dev set, on each iteration, you're only leaving out 1 over k of your data. I use k equals 5 for illustration, but in practice, k equals 10 is by far the most common choice that we use. I've sometimes seen people use k equals 20, but quite rarely. But if you use k equals 10, then on each iteration, you're leaving out just 1/10 of the data, 10% of the data, rather than 30% of the data.
Okay, alright. I think that's enough.
And so this procedure, compared to simple cross-validation, it makes more efficient use of the data because you're holding out
Data is small, we
10%
can
of
do
the
a
data
lot of
on each iteration.
computation.
The disadvantage of this is completely very expensive, that you're now fitting each model 10 times instead of just once.
Well, actually, with the data set, we had this assumption that data set is small. So I don't think it's a big issue.
But when you have a small data set, this is actually a beneficial simple cross-validation. If you don't mind the computational expense of fitting each model 10 times, this actually lets you get away with holding on less data.
Alright, I think we can stop here. I thought we could finish. Alright, have a good rest of the day.